let's take a look at very, very small time changes around 1 and 2 seconds, and let's see what happens. So over here we're going to have what we call h. Here we'll have t plus h. Yes. And then we're going to look at average speed in this column. Do one more. Well, we'll do this one first, and then we'll go to the time second. All right. So these h values: 0.1, 0.01, 0.001, 0.001. Okay. T plus h. We're looking at what happens at the first second here. So I'm going to put that t value in here, and I'm just going to add these things to it. So this is 1.1, this is 1.01, 1.001, 1.0001. Okay. And now what I want to do is I want to look at the average speed by using this t and this little bit of extra time above t. So I'm going to look at, in this instance, I'm going to take my 16 times 1.1 squared minus 16 times 1 squared. Divide that now by my change in time. My change in time is just the h value here, 0.1. And when I do that calculation, if you want to work along at home with us, what do we get? Let's see. Make this calculation, provided I can read my notes correctly. I should get something like 33.6 feet per second. So if I look at a very, very, very small window of change, if I look at what happens between the first second and the first plus 1/10 of a second, or sorry, 1/10 of a second. If I look just in that little small window, the speed that my thing that has fallen is traveling is about 33.6 feet per second. Calculation, hold up, math is validated for another day. All right, so let's do the next one. Let's take a look at what happens if we shorten that little time span even further. We now go to 1/100th of a second time change difference. How is that going to affect my average speed? In this case, hopefully, calculations are correct. We should get something like 32.16 feet per second. So, in this little smaller window we're looking at, it's traveling about 32.16 feet per second on the average during that little 1/100th of a second. That's how fast its average speed is. Right? If I continue on like this, let's do the next one. 16 1.001 squared minus 16 times 1 squared divided by 0.001. Do that calculation. Do you think that the average speed is going to go up or going to go down as we're shortening that distance? Go down?
It's going to be like 32.07.
Okay. Our average speed is shrinking a little bit. Okay? If we were to do one more, 16 1.0001 squared minus the 16 times 1 squared, 0.0001. This gets us even smaller average speed. Okay? Now, what do you notice is happening here? As we're decreasing this time change, what is happening to our average speed?
It's getting closer to 32.
It's getting closer and closer to the value 32, right? So you would expect that at t equals 1 second, at exactly 1 second after I drop this object, this right here is telling us that it's getting closer and closer to traveling at exactly 32 feet per second at that very instant. At that Very instant. That's how fast it's traveling. Okay? This is something that we'll work a little bit more with in the next chapter. We're looking at sort of making this educated guess that the map here is going to continue to follow this pattern forever and ever. Right? You would imagine that if I was to decrease h even further, that these values would eventually approach the exact value 32. Do we know that for a fact? I mean, our intuition tells us that that's true. But how do we know that maybe something really crazy happens when we get even further down here? Maybe at h equals 1/1,000,000,000th, it actually jumps down to 29. That would be terrible. But that's something that we'll focus on in the next chapter. Okay? So what's happening here with this average speed is that as we're decreasing these ranges, the average speed is being taken over smaller and smaller intervals. Essentially, what we're doing is we're taking that average speed and we're actually getting closer and closer to what's called the instantaneous speed. Okay? And that's something that we will focus on later on next week. Okay? Now, let me sort of take another picture of what this stuff is telling us, and I'm going to draw it in terms of a graph. Let me write our formula up here again. Okay. If I was to graph this function, we all know what the graph of this function looks like, right? What is it? It's a parabola, right? And for our purposes, we're only interested in the positive side because this has some real physical meaning here. We're only looking at what happens for positive time. It doesn't make sense for me to say that after -6 seconds, this thing has moved whatever 16.36. But we're only focused on the positive side. Now, if we look at what each one of these calculations is doing, what are these calculations doing? Well, the values on the top here, in terms of our graph, what are the values on the top? The values on the top are y values or t values? The values on the top of those expressions there are what? T. Y values, right? We're plugging the t in, and we're getting out a y value distance. Okay? So the top values over there are y values. So, for example, if this is our 16.1, and again, this picture's not going to be to scale. Bear with me. So there's the 16.1. There's the 16. The value in the bottom is a t value. So if I think about what this thing here is calculating, what is that value actually calculating in terms of our graph here? Change in distance over change in time. You can also think of this as changes in y's over, in this case, changes in t's. Have you seen expressions like this before? I hope so. What do you call it when you look at the difference in the y values divided by the difference in the x or t values? Slope. Slope of what? Slope of a line, right? And not just any line, but the line that connects the two y points that you're looking at. Okay? So this average speed that we've been calculating is actually calculating for us the slope of this line. The average speed is the slope of that line. And what's happening as we decrease our difference in t values, all we're doing is we're just taking that line and we're getting it closer and closer to the point we're working with. And eventually what we're getting is that if we get really close to 16, as close as we can, eventually that line hits this graph at just that single point. It touches the graph at that single point. Those kind of lines are what are called tangent lines. We'll focus a lot about that in the next couple weeks, how tangent lines relate to graphs like this and what their relationship to this whole average speed notion is. Okay. But in this particular case, this is what's going on with these calculations over here. Each time we change the distance between our initial point and our future point, we're changing the lines we're looking at, and what we're doing is we're just calculating the slopes of these lines. And we're looking at what is the slope of those lines as we get closer and closer to 16. All right. This expression, the delta y, notationally, sorry, this is also called delta y over delta x. That's what this little symbol is called. It's called a delta. So if you ever hear me say delta y over delta x, this is what I'm talking about. Expression-wise, this is y1 minus y2 over x1 minus x2. In this form, it should be readily obvious that this is slope of line. That's what the slope of line is. That's how we measure it. Okay.
So
Next up, go ahead.
when they show the delta sign, we automatically get the same slope?
Think of it as change. Don't think of it as slope, unless you see it as delta y over delta x. This is slope of line.
Okay.
If they just write delta y, that's just the changes in the line. That's not a slope, it just changes in the y as it goes. All right, next time we will finish 2.1, get into 2.2. That is all for today. So have a good day, and we'll see you back here on Monday.